This presentation treats the Hilbert Book Model project. The target of the project is the generation of a mathematical model that can be used in order to investigate the structure of the foundation and the lower levels of the structure of physical reality. I am a retired physicist. I spent my career in high-tech industry.
This lecture introduces you to the Hilbert Book Model. The model deviates considerably from the models that constitute contemporary physics. The model is strictly based on a trustworthy foundation. The Hilbert Book Model selects Hilbert spaces for that purpose. The model applies a system of Hilbert spaces. These Hilbert spaces all apply the same underlying vector space. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. A quaternionic Hilbert space can easily be structured as a dynamic model in which all past, present, and future geometric data are stored. Therefore, the corresponding space progression model becomes paginated like a book. It consists of an ordered sequence of static submodels. That is why the project got its name Hilbert Book Model. Please look at the book or paper, The Setbacks of Theoretical Physics. This is part 1 of a multi-part presentation. This part concerns humans, space, locations, vectors, vector spaces, and number systems. New items are phases, phase transitions, and symmetries of number systems. Humans cannot think and communicate about things without providing these things with identification in the form of a name or pointer and a short compact description. Physical reality can function without these limitations. Yet physical reality also appears to have to adhere to strict rules and existing structures. The researchers have come to know these rules and structures to a large extent, and they formulate them in what they call mathematics and physics. Several researchers doubt whether people can discover the calculation rules that physical reality uses. Your author does not belong to this group. When people focus their research on space, they quickly realize that an empty space represents the ultimate nothingness. There is nothing in this space to which one could orient oneself. There is no center and there are no boundaries. It's not hard to imagine that the space could contain many anonymous locations. However, for humans, it is not possible to track the behavior of these locations without giving them identification and a precise description. Locations are point-shaped objects that can occupy a position in space. That position differs per location. Identification can be achieved by using number systems. The values of the elements of the number systems can indicate the position of the locations. Locations feature a typical behavior that causes them to exist in different phases that switch via phase transitions. This influences their behavior as members of sets that use space as a container. There is still no possibility to point to the position. The pointer can consist of a base location and a pointing location connected by a direction line. Scientists call this pointer a vector and a space in which vectors occur a vector space. The vector has a length that can be characterized by a simple scalar number. The vector has a base point and a pointer point that both lay on the direction line. A scalar describes its length. A parallel shift along the direction line, or parallel to the direction line, does not affect the integrity of the vector. The vector may be displaced along the direction line. Or the vector may move in parallel in another direction. If the base point is shifted from one vector to the pointer of the other vector, then the non-overlapping points form a new vector called the sum vector. If the direction lines are different, the sum vector can use a new direction line. The two possibilities form a parallelogram. Vector addition is commutative. Vector addition is associative. Multiplication with a scalar is commutative. This multiplication may change the length and thus the integrity of the vector. It may create a new vector. Multiplication with negative scalars reverses the direction of the vector. In particular, inversion followed by addition introduces the procedure of subtraction. Multiplication with scalars is distributive for scalars and vectors. The length of a vector equals its norm. We call vectors with norm 1, natural base vectors. The norm follows from the scalar product of a vector with itself. Another name for the scalar product is dot product. For the scalar product between two vectors A and B holds. The angle alpha between the vectors A and B is measured in radians. To visualize this, the vectors A and B are shifted until their base points join. A zero value of the scalar product means that the direction lines of the two vectors are independent. Independent direction lines are mutually perpendicular. Direction lines can shift in parallel. They can form a grid. Humans can perceive lines. Humans can perceive two-dimensional grids. Humans can perceive three-dimensional grids. Humans cannot perceive four-dimensional grids. Mathematicians can reason about grids that have a higher dimension than 3. An ongoing addition of natural base vectors that share the same direction line generates a sequence of length values that represent the natural numbers. Coordinate markers indicate the location to which the sum vectors point. An ongoing addition of natural base vectors that share the same direction line generates a sequence of length values that represent the natural numbers. Coordinate markers indicate the location to which the sum vectors point. The natural numbers form a well-ordered sequence. The natural numbers enable the procedure of counting. The members of a set of objects are attached to a natural number. This also sequences the members of the set. The highest applied natural number represents the size of the set. Starting with the vector with the highest count, subtraction by a natural base vector represents downcounting of the involved natural numbers. At last, the initial natural base number is removed and its base point points to location 0. This enters the realm of the integer numbers. Further subtraction produces negative integers. Together with 0 and the natural numbers, this action produces the set of the integer numbers. The cross points in a grid can be indicated by a coordinate marker. The n-dimensional natural grid is generated by grid elements that are spanned by n natural base vectors that are mutually independent. N-dimensional natural grids can be used to generate a simple coordinate system for an n-dimensional subspace of the vector space. By adding groups of vectors several times, the procedure for multiplying numbers is created. That doesn't provide new integers. The reversal of multiplication is called division and delivers fractions. The fractions can be new numbers. The integer numbers together with the fractions form the rational numbers. Scholars have shown that there are as many rational numbers as there are natural numbers. This means that all rational numbers can be labeled with a natural number. This only works if both number sets contain an infinite number of elements. The transition from finitely many elements to infinitely many elements implies a change in state for the set. In the new phase, the collection exhibits different behavior. It is not possible to achieve this phase transition step by step. Also, the way back does not go in a step-by-step way. Adding or removing elements does not change the state of the infinite set. Phases and phase transitions are caused by the fact that space is used as a container of a set of locations, while the location feature a special behavior that introduce these phases and phase transitions. Mathematical sets do not commonly oppress these restrictions to sets of arbitrarily elements. This causes a difference between mathematical set theory and the set that is considered here. The infinite set of well-ordered rational numbers fills a large part of the same direction line. Any location on this line can be approached arbitrarily close by a rational number. Nevertheless, there are still many locations on this line that cannot be designated by rational numbers. We call the numbers that these places indicate irrational numbers. Together, the set of rational numbers and the set of irrational numbers again form a set that can be seen as another phase. The phase transition happens again in one go and cannot be achieved step by step. The new phase of the collection can no longer be counted. The combination forms the set of real numbers. These numbers fit on the same direction line. In this set, all series of converging members end in a limit that is a member of the set. The phase transition adds several new calculation rules that manage the change of cohesive parts of the collection. Mathematicians call these extra calculation rules differential calculus. We will indicate the real numbers with the suffix r. For first phase real numbers, addition and multiplication are commutative, associative, and distributive. In the second phase addition and multiplication only work for first phase members. Quadrature is positive or equals 0. Multiplication with the same number is called quadrature. There also appear to be systems of numbers that, when multiplied by themselves, yield a negative scalar. These numbers are often called imaginary numbers. We will not use that name. We call them spatial numbers. Because imaginary is a confusing qualification. The spatial numbers no longer fit on the direction line of the real numbers. They occupy 1 or 3 dimensions. This is because if spatial numbers fall outside the first spatial dimension, the calculation rules of the spatial numbers ensure that in addition to the second spatial dimension, a third spatial dimension is also filled with spatial numbers. The result of the product of two spatial numbers consists of an internal product that provides a real number and an external product that is 0 or produces a result in a direction that is independent of the direction lines of both factors. The internal product is the reason for the negative square. The calculation rules of the spatial numbers, therefore, differ from the calculation rules of the real numbers. For spatial numbers, addition is commutative and associative. The product D of two spatial numbers A and B results in a real scalar part dr and a spatial part D. The scalar dr represents the inner product of A and B. The spatial number D represents the outer product of A and B. For the inner product and the norm of A holds. The angle alpha between the spatial numbers A and B is measured in radians. The square of a spatial number equals 0 or it is a negative real number. This formula represents the outer product of the spatial numbers A and B. The spatial part is independent of A and independent of B. This means that the inner product of A and D and the inner product of B and D both are equal to 0. In addition it is possible to write spatial numbers as superpositions of base numbers. For the three-dimensional spatial numbers, this means the plus-minus sign indicates the chiral choice of the handedness of the outer product. The three natural base vectors I, j, and k in formula correspond to a Cartesian coordinate system. Also, other coordinate systems exist. In this presentation we also use spherical coordinates. The spherical coordinate systems used by physicists is shown here. See Wikipedia. The mathematicians use the presentation shown here. What mathematical physicists apply can only be guessed. Spherical coordinates, r, theta, phi, as often used in mathematics, radial distance r, azimuthal angle theta, and polar angle phi. The meanings of theta and phi have been swapped compared to the physics convention. As in physics, ρ is often used instead of r, to avoid confusion with the value r in cylindrical and 2D polar coordinates. In the Hilbert Book Model we follow the mathematicians, but we use r instead of ρ. We don't use cylinder coordinates. The three-dimensional version of the spatial numbers system exists in more variations than the one-dimensional version. The reaction to a disturbance of the third phase of spatial numbers is more spectacular in the three-dimensional spatial number system than in the one-dimensional spatial number system. Symmetries represent the freedom of choice that is not defined by the calculation rules. As a result, the number systems exist in many versions that are distinguished by their symmetry. For example, the location of the geometric center of the number system can in principle be anywhere in the vector space. Also, the arrangement of the numbers can proceed along the direction lines in one direction or the opposite direction. Symmetries exist as geometrical symmetries and as arithmetic symmetries. Physical reality must adhere to the rules of calculation and will use as many symmetry choices as possible. A different choice of symmetry yields a different version of the number system. The word symmetry has several different meanings. This also occurs in this presentation. In the Hilbert Book Model, the azimuth phi is restricted to the interval -180 degree to +180 degree, or -yo plus pi in radians. For theta, we use the range -90 degree to +90 degree for elevation. This choice is in correspondence with the choice for the chirality of the outer product. In the considered circumstances, the location density distribution is often called a point spread function, PSF, and its Fourier transfer is called optical transfer function, OTF. These functions play an essential role in the qualification of imaging processes. The range of the inclination angle corresponds to the selection in the chirality of the outer product of the spatial numbers. This marks the chirality choice as a geometric symmetry. Counting and downcounting can be applied to spatial numbers. This relates spatial numbers to natural numbers or other integer numbers on the natural number direction line. This leads to mixed number systems. Counting one-dimensional spatial numbers leads to the two-dimensional complex numbers. Counting three-dimensional spatial numbers leads to the four-dimensional quaternions. Counting or downcounting randomly distributed locations that are identified by coordinate markers, inside an enclosed spatial region, generates a hopping path. The path has a given path length. The path length corresponds to the size of the set of hops. The hopping path is not a set of vectors, but the switching locations can be pointed to by a set of vectors or a dynamic vector. The progression of the dynamic vector is then indicated by a natural number. Progression might run up or down. So negative numbers may be involved as well. Nothing is said about the process that randomly spreads or indicates the locations that are marked by the involved coordinate markers. When the size of the set of hops grows, the chance becomes larger that some of the involved coordinate markers are used multiple times. This means that at each reuse the hopping path gets closed and after that the path proceeds. If the reuse happens at regular periods, the hopping path is called recurrent. If the stochastic process that generates the locations possesses a characteristic function, then the recurrency cycles of the hopping path own a location density distribution. The location density distribution can be determined by covering the sampling aperture with a natural grid and counting the locations in each of the cells. The location density distribution owns a Fourier transform. The nature of the stochastic process that generates the locations of the hopping path is not known. We can only guess. We think that the process is a combination of a Poisson process and a binomial process. The binomial process spreads the efficiency of the Poisson process over a region of the spatial number system. The binomial process is characterized by a location density distribution. If the location density distribution focuses around a single maximum, then the location density distribution gets the shape of a normal distribution. This is also the shape of a Gaussian function. The Fourier transform of a Gaussian function is again a Gaussian function, but it owns a different relative variance. These relative variances relate via an uncertainty relation. This does still not explain what the origin of the Poisson process is. For the author, it is a mystery. It has something to do with the coupling between the vector space and the spatial number system. If in a recurrent hopping path, the size of the recurrent and periodically recycling subpath is getting large and resembles a normal distribution, then the coordinate markers of the involved hop landing points will show as a focused spot. In nature, such spots often occur in images. The skew hop can be split in 3 parts that run along grid lines. This increases the number of hop landings and the size of the hopping path. So, hopping paths exist in different versions. Mixed numbers are indicated without suffixes and caps. In the next formula, C is a mixed number. The addition and multiplication of real numbers with spatial numbers are commutative. Quaternionic multiplication obeys the equation. The plus or minus sign indicates the freedom of choice of the handedness of the product rule that exists when selecting a version of the quaternionic number system. In this way, the handedness of the outer product is treated as a special kind of symmetry. The outer product does not occur in complex numbers. The version must be selected before it can be used in calculations. Two quaternions that are each other's inverse can rotate the spatial part of another quaternion. The construct rotates the spatial part of B that is perpendicular to the spatial part of A over an angle that is twice the angular phase theta, where the complex number arat equals where the transform C equals A times B divided by A rotates the spatial part B of B around an axis along the spatial part A of A over an angle 2 phi that is twice the argument phi of A in the complex number system that is spanned by I and 1. Symbol B with subscript parallel lines means parallel. Symbol B with subscript perpendicular lines means perpendicular. We were able to generate number systems by applying the arithmetic of vectors. This approach introduces geometric symmetries that are not encountered when number systems are developed in the traditional way. The generated number systems appear to exist in several phases. Phase transitions cannot occur in a step-by-step fashion. The phases have their own arithmetic. This is caused by the fact that the set elements are locations and space is the container. The generated number systems can be mixed. Together they constitute the associated division rings. This covers the real numbers, the complex numbers, the quaternions. Each of these number systems exists in multiple versions that differ in their geometric symmetry. Stochastic processes can generate hopping paths. The hopping path may recurrently generate a hop landing distribution. The hop landing distribution might own a stable Fourier transform. The footprints of a state vector represent such recurrently generated hop-landing distributions. The foundation of physics can be represented in a single sentence that reflects the structure and behavior of the observable universe. The universe that manifests itself to researchers is one continuous film of the possible coverages of space with versions of number systems belonging to the associative division rings. The experimental particle physicists discovered that fermions exist in several, probably 3, generations. The Hilbert Book Model project interprets this as if 3 generations of locations exist. It looks as if space is applied as a container. The set of the locations exhibit special behavior, which results in multiple phases and multiple generations. This differs from the more general set theory that mathematics adheres. This ends part 1 of a multi-part presentation. This part concerns humans, space, locations, vectors, vector spaces, and number systems. New items are phases, phase transitions, and symmetries of number systems. Part 2 will concern phase 3 of the number systems. Part 3 will concern other field equations. Part 4 will concern Hilbert spaces and systems of Hilbert spaces.